now I have to say something about the speaker. Our speaker is Matthew Borgatti, and he's the founder of a company called Super Releaser. And what they do, they are building spacesuit components, robotic spacesuit components for NASA, and they're researching and developing on a field called soft robotics. So Matthew will now talk about soft robotics. So I'm not sure, but I might give you this hint. If you're close to him, don't try hugging everything, because this robot might crush you with its soft, delicate hands. A warm applause for Matthew.
Hello. Yeah. I've got to clarify, I'm a subcontractor on a NASA project. NASA doesn't like it when you say I'm working for NASA unless you are in their offices. I've just got to clarify that, because people who can laser you from space, So Einstein was on a train, and he turns to the passenger next to him and says, "Does Boston stop at this train?" So why can't programmers tell the difference between Halloween and Christmas? Because 3-1 oct equals 2-5 dec. Okay. All right. So I'm the founder and lead scientist at Super Releaser. Super Releaser is a soft robotics development company. Essentially, we solve hard problems with soft robots. Soft robotics is a new field of robotics. It's pretty young, only about 30 years old. And the heart of it is most problems that get solved with biology, most problems that get solved in nature, are done with compliant materials, squishy stuff. And most problems that are solved in engineering are done with hard things. So hard languages, hard actuators, things that don't have much give, things that don't have much compliance. And it essentially means that half of all potential solutions to problems in robotics have never even been considered. And so that's what I'm excited about, and I'm excited especially about applying it to human scale problems. So I'm going to be talking about some of what our work is, the uses for soft robotics, and how to build your own. Okay. We're going to start with a little brain teaser. So your skull is wired this way. You have a hinge in your jaw. You have this mandibular hinge. And the muscles are connected from your temples down to your jaw. If you feel the sides of your head and you clench your teeth, you can actually feel those mandibular muscles flexing. And so you can actually generate 200 pounds. The average person can generate 200 pounds of bite force from their jaw. That means if you stick your tongue out right now, you can bite it clean off, which is cool. You really can. Don't try. So how would you do this? How would you bite things without a skull? So there are actually creatures out there that do this, squids. So squids have a beak that's very hard. It's a bird-like beak. It's really unusually bird-like. It's an example of convergent evolution. And they don't have a skull. They actually don't have any hard understructure whatsoever. And they can bite things that are actually many orders of magnitude harder than they are in half. They have a body that is about as firm as a tomato, and yet they're able to bite through fish. And the way that they do this is through something called functional grading. So up at the tip of the beak, what's called the rostrum end, they have a very hard end, the very hard proteins, hydrophobic proteins that don't have much water in them, that blend out towards the wing end of the beak, that blend out to softer and softer, more water-bearing proteins as the thing goes down into the squid's head. And that's met by firm muscle tissue that comes onto the wings, and then it distributes the force up through the mantle. So what ends up happening is you have this very hard tip here without a fulcrum. It's actually balancing all of those forces of biting across the structure, using distance to balance that force and to get lots of clamping pressure on the end of that beak. So what am I talking when I'm talking about applying this stuff to human scale problems? So I trust you can read. I'm not going to individually talk about these points, but just to say the cost of having cerebral palsy is very high. And a lot of that is because physical therapy with one-on-one with the therapist is very expensive. And the orthotics, the things that you use every day to try and get you more mobility, have to be customized, tailored to every individual person. Now that ends up being very expensive because specialists have to do this work. So the reason why it's sort of a complex problem that's not easily solved with a traditional exoskeleton is human beings don't really have a hard, rigid ball-bearing joint in, say, the elbow. We're not made of these hard linkages. They're softer. These are actually two surfaces that are not quite cylindrical, riding over one another. It's not just a fulcrum. And every body is different. Every person's a little bit, they've got a little bit of different muscle tone. They've got a little bit of, different something. They're different diameters. And so it's hard to make a one-size-fits-all robot in a traditional robotic sense. But what's also the case is that customizing it for a person takes a particular expert, someone who knows that particular robot very well, to center its power. Say if you're trying to have an elbow actuator where there's a pancake motor right here and it's actuating your arm out. It actually takes somebody to get that right there as close as they can to the pivot of your elbow so that if it can't come a little bit off of the joint, otherwise it stands the potential of hurting you. It can actually do more damage than it's trying to fix. So that's one thing that we've been working on at Super Releaser is soft exoskeletons for therapeutics. So can I get a volunteer? You. Yes, please come up. What's your name?
Robin.
Robin.
Hi.
Round of applause for Robin, please. Yes. So, would you mind trying a unlicensed medical device? Oh.
Definitely.
Groovy. This and arm. Could you please put your arm through here? Thank you so much. All right, so the problem we're trying to solve in cerebral palsy is the point of your elbow on the point there.
That's what I'm thinking.
Yeah.
Not quite.
Well, let's move it up a little bit.
That's great.
How's that feel?
Yeah, that's great.
Groovy. So I wasn't able to take my, my compressed air supplies through the airport for obvious reasons, but I'll make do with a hand pump. So the problem we're trying to solve in cerebral palsy is that you have essentially high muscle tone, that you're stuck like this. And what we're trying to do is give even pressure to get your arm back out. So just tell me what you feel as we go through that. So what's happening here is that we have these soft actuators that are distributing force over the arm. You feeling a force?
Yeah.
Hey! Please give her a round of applause. Thank you. Thank you so much. So the concept is one size fits all pneumatic exoskeletons. And what I think is cool is that this compliant, squishy, squid-like way of thinking about mechanics means that you can do things in these one size fits all ways. But what you can also do is sort of compensate for the irregularities of individual human bodies. So other researchers are actually applying this to really interesting problems in like stroke rehabilitation, giving people higher muscle tone, able to like grip with more force, recovering from strokes. There's a place called Other Lab in San Francisco that's literally making a squishy Iron Man suit. And what I think is really cool about it is that if you can encourage people to do daily tasks as someone has a physical disability like cerebral palsy, in giving them a little bit of extra freedom can mean huge lifetime gains, because being able to grip crutches, being able to dress yourself, enables you to do a whole bunch of things that also motivate you to continue using your muscles, to continue refining skills. And so little changes to mobility can have a huge change in overall health. So other ways people are applying functional grading to problems are with like explodey soft robots that has a soft structure and a rigid structure. So you can get things that are soft and rigid to do to solve particular problems. And one way this is really applicable is in prosthetics. So this is a scan of Hugh Hare, Hugh Hare's leg. So Hugh Hare is a double below-the-knee amputee who works at MIT. And he's been working on these projects where he takes scans and he 3D prints functionally graded structures that distribute the force of the impact from the prosthetic onto the residual limb. Now, the reason why you want to do this is people are made of mostly water. People are made of mostly water, and any impact does not get dissipated by some cushioning force. There's not a cushioning spring inside of the body. So when you have a residual limb, you have an amputation, you have a residual limb, your doctor tries to do the best they can to make it susceptible to a prosthetic, but it doesn't mean it's infinitely powerful. And so what happens is when you feel a shock, say, of walking upstairs from the prosthetic socket, into the residual limb, none of that force is dissipated by the socket. To get it registered onto you, it also means that waves of force coming up through the prosthetic sort of find all the tender vittles. It's not a pleasant experience, and what's difficult is that can cause the residual limb over time to break down. So scar tissue isn't terribly strong, and so it has this feedback loop. A socket for the residual limb, the interface between the prosthetic and you, has to be particularly shaped to you, but if it damages you, you change shape. And so what they're trying to do is create a system where it dissipates force. The socket itself is strong enough to support the force from the prosthetic without pushing all of that force onto the easily damaged area of the residual limb. And so Hugh Hare is using functionally graded structures to do this, 3D prints that have very high levels. The white is very high levels of stiffness, and the black are very low levels of stiffness, so we can choose where the force is distributed. So another organism, another mechanical system that does this kind of distributed force to solve problems very well are goat feet. So goats don't spend a lot of time looking at their feet. They're actually able to put their feet wherever they want. Say it's slidey rocks. They put their feet where they want, and they don't stare at them to figure out what they're doing. If you've ever seen Asimo walk upstairs, it spends a lot of time looking down, being like, okay, feet, what are you doing? And it has to position the foot to land precisely on the step with the right angle, or else it'll slide right off. And that's because the system doesn't have compliance in it. Working with actuators and servos, it's often difficult to have them embody compliance, to be squishy. And so it's hard to get them to deal with unknown situations, and oftentimes you have to pause a robot in its tracks so it can look and assess its situation before moving on. So here are goats, also goats. And here's a robot. So what I'm trying to solve here is, see, you notice its feet are hard metal pads. That's insane, because it can't possibly compensate for unknown situations. If it's moving forward, it has to land with its foot at the correct angle. If you remember physics, vector forces, yada, 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 it has to land with its foot at the correct angle to compensate for the force of the forward motion on whatever it's landing against. It's a very difficult problem to solve purely computationally with hard actuators, but it becomes simpler. You can do it in a stupider way if you just arrange the matter to move in a certain way when there's force. And another organism that solves this very well is bugs. So flies have these things called setae on their feet. They're spatulated hairs. What the fly will do is it'll drag its foot down a surface, and it can even be a really smooth surface like glass. And it'll drag its foot, and the itty-bitty hairs, those are incredibly tiny. That's a tiny fraction of the size of a human hair, will actually find little cracks and microstructures inside of the surface, and it just drags its foot down until the foot catches. And it just has this algorithm that is like drag down foot n until it catches, and then start that process again with n ++ 1. And it just does that for all feet, and then it does that again. Flies aren't known for being very smart. And so the way we're trying to employ this in soft robotics, this represents some of the work I actually got to participate in with a NASA researcher named Aaron Parness. He's not called Aaron Parness, he's named Aaron Parness. Where we're trying to do this thing where we can mass manufacture these guys that have a complex behavior that when you put them all together, so the individual actuator is really easy to make, or the individual mechanism is easy to make, it's easy to multiply them. And so you can get interesting behaviors by multiplying that to have hundreds and hundreds of these all working in tandem. So the way this works is there's a rigid structure here, bringing up the squids again. There's a soft structure here, and then it has two mounting points so that you can essentially load the spring on it. And what happens is this grips in when force is pushing down, but as soon as it's unloaded, it'll pop back up. And the way that these are used is in big blocks. What Aaron's trying to do is he works at JPL to try and make NASA exploratory robots to climb over rocks in Mars without having to ask NASA all the time, what am I supposed to do with my feet? Because it takes, I think it's 14 minutes to relay that signal to Earth and then time to get that back, and that makes exploring very, very time consuming. But And this, I didn't flip this GIF over. This is literally upside down. And so what's happening here is you take all of these hooks and you have this incredibly simple procedure, which is take the paw, move it over, grip the paw until the paw has caught, and then you're done. So I'm going to show you how to make your own soft robots. So these are not sex toys. They are soft robots. So I do a lot of 3D printed soft robots. I publish them in the open source. I have a lot of stuff on Thingiverse. You can look me up, Giant Eye, Thingiverse. I am actually writing up a book for Make on like every soft robot I can think of, so it's all published in one place. You know, yada yada, buy my book. So it's not even out yet. So it starts with, you can actually use 3D printing. I figured out how to watertight print with an FDM printer, so I can use cheap prints to make things watertight so you can just make molds. And what's cool about that is I can make generations of molds that all experiment with different ideas and make them all at the same time and label them like experiment A, B, C, D, E, and then cast them all, evaluate them against each other and not waste too much of my time, because my time is precious. I can buy robots to do the printing. So it's a mold that's sort of like two halves. I'm not tall enough. Anyway, so the mold is two halves. And there's a core in the middle. And the silicone is squishy enough that once it's cast, and so this is a little gasket here that you'll see coming into play in the end. When the mold is assembled and the silicone is cast, I can actually pull the core out of the silicone. So there's a structure on the inside of the silicone part. There's a structure of a void. So I'm choosing where to put the not silicone. And when that inflates, it actually distorts the silicone in a certain way. And so what'll happen here is, here's the part that gets mounted on. Remember, there's only silicone and air there. And then it makes this kind of complex gripper. And so I'm going to try to, again, don't have my air supply here, so forgive me for not being macho enough to really manage this. But, all right, gripper. All right, do it. Yeah! Yeah. Anyway, so it's able to pick up a big variety of objects, and by just being simple and squishy, because it squishes around the object. And so that compliant, conformal nature makes it good at just sort of picking up stuff. All right. So the last thing I want to talk to you about is our work at NASA, and another way to do soft robots for human scale problems. So as you might know, space sucks for your body. Space isn't very fun to be in. It's exciting, but not terribly fun physically. So being in zero gravity like spherizes your heart over time. The surface tension of water becomes a dominant force, and so your eyes spherize. There's a particular kind of astigmatism that happens in space because your eyes, instead of being initially, the eyes are a little bit egg-shaped, they'll actually turn into spheres and you'll get nearsighted. Everybody in space wears glasses. And so one thing that's really difficult is to make a spacesuit. Essentially, what you're making is a soft, human-shaped spaceship. And what's difficult about managing that is the softness is there so you can do stuff with your many points of articulation in space to do things like repair the Hubble and stuff. But what's difficult is because there has to be air pressure, you evolved at the bottom of a gravity well. There's a giant air column above your head that reaches out into space. That's all of this air pressing down on you. And when you let all of that off, everything in you essentially swells up. Your veins dilate. And it sucks a lot. Literally. So, no. So anyway, what happens is your body doesn't work well in a vacuum. And so what we've done in usual spacesuit design is to replace that atmospheric pressure that you would otherwise have in a gravity well with pneumatic pressure. We have a big airtight suit, and we inflate it to like 7 pounds, and that's that. What's difficult is that becomes a giant air spring. If you've ever blown up a rubber glove, you'll notice that it's springy. So the suit springs back, and if you're doing delicate labor with your hands, it actually is really terrible. People's fingernails literally delaminate from their nail beds, and their gloves fill up with blood as they're working on the space shuttle, as they used to work on the space shuttle, because the glove design actually causes you to essentially push against this spring constantly. Now, how would you solve that? Currently the glove is sort of like this. So this is like, imagine glove is in a vacuum chamber, and you're putting your hand inside of the glove in the vacuum chamber. So in the current glove, we fill it with air. So we just extend the regular atmosphere into the vacuum chamber. If you put your bare hand into the vacuum chamber, your hand would get all purple and swollen. And there are other ways to solve this. Like you could have a perfectly cast like steel hand void. So there could be a steel block with a hand-shaped hole in it. You grease your hand up, put it in the steel, and when the vacuum chamber vacuums, your hand wouldn't change shape at all. And so you wouldn't experience the vacuum. But that's not very useful for like repairing spaceships. Another way to think about it is there's pressure coming out. So what if we put pressure coming in? You can actually make really small, stretchy gloves and have somebody put their hand inside of the really small, stretchy glove. And then when you turn on the vacuum, the pressure in will equal the pressure out, and that's called mechanical counterpressure. And so that's what essentially we're doing. Here's the Gemini-style glove, so that's the big bag of air, and here's the mechanical counterpressure glove. The mechanical counterpressure glove is made of elastics. They're actually biased to be a little bit small, and that provides the exact same pressure in as space is pulling out. Now, the way you get your hand into these is we actually use some soft robotic elements to change the size of the glove so it's a little bigger when you put it on, and then you shrink the glove with pneumatic pressure until it's sized to fit your hand. And so the part that I'm specifically working on, spending most of my time on, is this is going to go into space. Well, if everything works. So the idea is not to make a mechanical counterpressure suit in one go, but to do it incrementally. And so we're putting it onto the current NASA ISS suit using an interface from the regular pressurized suit out to the glove that's actually open to vacuum. So the glove protects you from the vacuum pull of space, but it actually doesn't need a bunch of air around your hand. So what's interesting is we have this pressurized suit and this depressurized glove, and to transition between them, what my lab super releaser is spending the most of their time on is a gasket that takes you from the suit pressure to the zero glove pressure without cutting off any blood to your arm. It's a cool problem and a cool interface and a cool problem to solve. And we're doing this with fancy 3D printed molding with magnetic cores, and what I really like about it is the engineering is complicated, but the materials are so cheap. So anyway, I'm Matthew Borgatti. This is my company, Super Releaser. Please get in touch with me if you want to solve hard problems with soft robots, and I'd love to take any questions you have.
Okay, thank you very much. So I think we will follow the usual Q&A pattern, and while you are lining up behind the microphones, we will start with the Signal Angel.
Hi. So I have two questions from one person, and the first one is there a hand prosthetic version of the Mars robot Flyclaw? I'm sorry.
The Mars, the Claw Explorer?
Yeah.
Is there a hand version, like a human hand kind of version?
A hand prosthetic.
Oh, is there a prosthetic that works like that? I've never seen one. I mean, it's totally doable, though. Oh, I did literally work on a project to do this. I worked on a show called Prototype This. That's how I met Aaron Parness, is we literally made a Spider-Man suit that used these to, a person had ones on their hands, so I'm changing my story. So we made hands that a person could climb a wall with to give them Spider-Man powers. So it has existed at one point in the universe.
And the other question from the person was, are shock absorbers for prosthetic legs available, or is all the compliance at the attachment to the body?
So it's kind of a complicated problem. So you might notice the recurve legs. Have you ever seen the running legs, like the carbon fiber spring legs that runners in the Paralympics will use? They have integrated shock absorbers. It's a compliant shock absorber. But the difficult thing is, you can imagine, to absorb shock, you need to move mechanically. And so since the force is coming up, you need to move down. And so if you had just a spring, so you can imagine like a piston leg, you'd have a spring, and every time you step, to absorb the shock, you'd end up having a very odd gait, which might be acceptable, might not be, but it's a suboptimal gate. And so the way it's currently attempted is by having silicone sleeves that get you between the prosthetic sleeve, which is usually hard carbon fiber, and the residual limb is a silicone sleeve. But the problem is it doesn't dampen any of the force. And so the idea is to not absorb shock by like having the prosthetic go down, but distribute the shock to the strongest possible places in the body, to distribute it to the strongest places in the residual limb instead of distributing it over the entire residual limb.
I hope for Portal-like jumping of buildings too.
Boing.
Another question or the microphone? I think we have no questions at the microphones.
Well,
All right, I answered everything.
Then
I
another
still have
signal.
one here,
Yeah.
if nobody else wants to. Another question from the IRC is, as like designing silicon circuits is quite complicated due to the variability of process parameters. How do you predict the elastic behavior of your robots, e.g., for example, by FEM simulation, or do you just do trial and error?
Yeah, so it is sort of amenable to finite element analysis, FEA, but it is actually really processor intensive, and you can do things that are like works-like models. So you can take meshes and you can distort the mesh in it, and it's a very nonlinear system where some distortion changes the wall thickness. You can imagine an inflatable thing. The walls get thinner, and so that changes the dynamic of the system, and you have to recalculate. What ends up being difficult is having that be accurate to the world is tough. And so you can have simulations that give you some predictive power, but there isn't anything where it's a good design tool that also features simulation, where it's accurate enough to really predict this is going to do that. I did it. The words on the computer matched the world. And so I've designed successfully. What ends up happening is you use some of those tools, and then I've found it's best to have frameworks where you can iterate, where it's simple to modify, because the simulation will never be as informative as experimentation. There are technical documentations, the amount of stretchiness in the silicone, and you can predict this to a degree. But I found the best way is to iteratively prototype and lower the cost of making a new prototype by making it really quick and really cheap. And that ups the amount of prototyping you can do.
Okay, thanks. And as a follow-up, like how much does the material properties vary? Like is the variation really high, or?
So silicone is very consistent. So I use RTV silicones. Room temperature vulcanizing, you can get them. They're two-part silicones. You mix them together. And the chemistry on them has advanced to a point at which you just 50-50 mix them and they cure. And their properties are they're very consistent. Their variability is documented. It's usually fairly low. Some of it requires a little bit of process control, where if you're very diligent about it, you need to make sure that there are no bubbles in the casting and that your casting is dimensionally accurate. There are all these mold-making tricks and techniques. There's sort of like Adam Savage model-making tricks and techniques of like you got to tip it to the side to make sure the bubbles get out in this direction and stuff. But it's very consistent. Groovy.
Okay, then we have actual people behind microphones. Not that the people on the internet aren't actual people.
They're not, right?
But these people are around here, and since we have a lot of time, you have left. We can have more questions. We can have more questions from the internet. But first, a few questions from the microphones.
Yes.
Hi, yeah.
Is that one on?
Do I need to turn this on? Test. Okay, whatever. You mentioned before that the resources are really cheap. Where do you get your resources? I don't know what, in comparison to what. I don't have any huge funds to research with. Where do I get my materials? How do you deal with getting a specific shore? And do you work with shore? I don't know what your material specifications are, and have you mixed different components together? How would you advise we do this at home?
Okay, so to break down, where do I get materials? How much do they cost? Do I combine silicones, and sort of what like range of durometers am I looking at?
Sure.
Groovy.
Also, do you have... I'm sorry, I have done a lot of research and I haven't found any answers, so I'm asking you. Conductive silicons, have you found any? Do you have any solutions?
Oof. So conductive silicones, if you look at dielectric elastomers, and it's spelled D-I-E, like dielectric elastomers, dielectric elastomers, there is some documentation on them. They tend to only be conductive in very high voltage ranges, like plus minus 500 and up. But they do exist. I tend to discount them because it's sort of not my field. There are some people who are working in soft robotics who use shape-changing elastomers for that use an electric shape change effect. The materials I'm using, I have an FDM printer. I use an Ultimaker 2. I use whatever cheap PLA I can find on eBay. I use SaneSmart a lot. The silicone that I use is Smooth-On. I will use Smooth-On Dragon Skin 10 and EcoFlex 0050. They are about $100 a gallon. But they are much cheaper than the technical silicones you'll find for medical research and medical implants. Those end up being $100 a pint. The adhesives I use, there's a adhesive Silpoxy that Smooth-On makes. You can also use epoxy silicone caulks that you find from Home Depot and stuff like that. The Shores that I'm using range from 0050 to Shore A40. I'm usually around the Shore A10 region. You can thin silicones out with silicone oil, and you can also buy thinning agents from silicone manufacturers. And EcoFlex is miscible with Dragon Skin because they're both platinum cure silicones that use the same filling agent. And so I mix them oftentimes at a 50-50 ratio to titrate the durometer. Yeah.
Smooth Skin doesn't have any European distributors. Do you have any solutions?
Oh. Amazon?
Import?
Tor for physical objects? I don't have a solution for exporting. I would call them up and ask nicely.
Thanks.
All right, so we saw you using that hand pump to close that
Yes.
hand claw prosthesis
Thing.
Yeah, so I'm just imagining that on a human being, for example, how much air pressure would you need to actually make a responsive hand prosthetic, and like how much air pressure would you need for tasks like lifting a jug of milk, like a gallon of milk, for example? And would it be feasible to install all the hardware you would need to generate that pressure on a human being on Earth, and as opposed to space?
Relevant questions. So my devices tend to articulate from about 10 to 20 psi. I use compressed carbon dioxide canisters, which have about the power density of a lithium polymer battery. So if you look at grams per joule, they have about the same power density. So I tend to use them, especially because the torque is instantaneous. They come if you've ever reinflated a bike tire. So it's those emergency bike tire reinflators, or if you're San Franciscans and like doing whippets, it's those things. And I think the systems that I've made to compress them into like human scale usable things, you can't take compressed gases on planes, whatever. But I think that the power density is appropriate for articulating objects in this domain. People have worked in them. Other lab has worked in that. Getting lots and lots of force out of things. Like if you want to pick up a jug of milk with just compliant mechanisms, like you're starring only silicone, that's a more difficult problem because you have to stiffen the silicone to the point at which it can like resist the weight of the gallon of milk. But a way to get around that problem is to put spines inside of things. So the way nature has done that is when things need to have a lot of torque, they'll actually put spines in things, and the spines will help keep distortion, like linear distortion, from being a detriment from the total amount of force that you have in the system. And so, snakes do that. Snakes solve that problem with spines. But you sort of have to choose your battles. It's not a perfect solution for all problems. It's a good solution for compliant interfaces, but you have to sort of choose your battles, and I look to nature to do this, to figure out what mechanisms are appropriate.
All right, thank
Thank
you.
you.
Okay, I heard we have more questions from the internet, from nice people from the internet. So if they
Yeah.
could be
Or from a
red.
fridge, you never know. So, we have one question here. How do universal jamming grippers compare to articulated grippers? This is quite special, I guess.
Yeah. Okay, so a universal jamming gripper is essentially a balloon filled with coffee grounds. If you ever bought vacuum-packed coffee, it is like a hard brick until you pierce it, and then it turns all soft. And that's because without any air to have the individual grains, the granules to move past each other, the thing solidifies. And so you can get conditional stiffening by pulling out or putting in air. And so universal jamming grippers are rubber balls that have coffee grounds inside of them, and then when you suck the air out, they stay in whatever shape they are. And so if you squish it over an object, then suck the air out, it'll pick up that object because it's stuck around it. And so it can even be a straight-sided object like a dice, dice, the name for one of those things. So even if it's a straight-sided thing being rubber, there isn't any draft on the individual random number generator to actually pick up, or it can't drop right out because of the friction on the walls. So the advantages of those is they can pick up a huge variety of objects, even things that are like really flat on tables. The disadvantage is they get pierced pretty easily. And that's a problem sort of all pneumatic compliant systems, but they get pierced pretty easily, and there are categories of objects that they can't pick up, so anything that has like a handle that you have to get all the way around, because there are disadvantages for using the jamming gripper too. So if it's really tall and you want to squish it over a handle, you need enough space to squish it over a handle, it'll actually distort a lot because the more space, more distortion. And so as you pick it up, it'll actually be like bleh, and let go of heavier objects. One of the advantages of like the Soft Robotics Incorporated gripper is that the octopus tentacle style grippers, the digital hand grippers, are good at like wrapping around things like a couple of times, or wrapping around things with handles and picking them up. Their disadvantages is they're not very good at like picking up a penny. They're very bad at that.
You have more questions for us, or?
I think.
Yes, I have a question, as we have still quite some time.
Oh, no.
I guess it will take a bit. So, how does one build small, lightweight sources of pneumatic or hydraulic pressure?
Got it, yes.
Really small.
Yeah, so that's a problem I'm actually trying to work. So there are ways of getting small amount of pneumatic pressure with piezos. So what you can do is you can have a closed volume, goodbye computer, anyway. So you can use piezos that essentially have two check valves, and the piezo is pushing into this airtight container, and it'll push a little pressure out of the check valve, out of check valve 1, and pull a little pressure from check valve 2, and they can articulate very fast, and it'll generate pneumatic pressure. The disadvantage is it's usually not that much, and you have essentially a spring system in there where if the pressure, the back pressure, is more than than the piezo can overcome, then it peaks out at pressure. And so that's a way of getting really, really tiny pneumatic volume or pneumatic stuff going on. It's essentially imagine taking a piezo speaker and then putting a couple of check valves in a thing. You can have like a printed enclosure for it. And that would be a really tiny way. The other ways that it's usually done is you have diaphragm pumps. The small, cheap ones that you can get from China are these diaphragm pumps that just use a rubber diaphragm, and they push pistons that are actually all on a pivot. And so they'll go around, and the diaphragm will push in and out, and check valves will cause the pressure to continuously go out. And so that's the way that's done. Small hydraulics, are not super my field. I don't know that terribly well. My solution for that has actually been to use pneumatics to displace hydraulics, to sort of like you can imagine bubbling air up into a soda bottle and then having a straw with the hydraulic end going down. And that's how I handle hydraulics.
Okay, I have just realized how long you've been standing there. So the microphone, please. And why didn't get anyone a human chair or something?
I heard that if you let robots roam a forest, then they break something after like 5 minutes, and they will destroy themselves pretty soon. So could soft robotics also be a solution to this problem?
I think that it is. So to like wrap it up, to wrap up that question in sort of a bow, Boston Dynamics makes this really expensive robot called Big Dog. And I'm not here to like, Boston Dynamics, rah, because like, who am I to talk? I make these, like, I'm not super sophisticated. But one of the disadvantages is it's a complicated robot with lots of things to go wrong. And one thing that can be very difficult in having it operate for an extended length of time is that it has to make all of its guesses exactly correctly to not like topple over. And it's supposed to like keep soldiers from dying and going into dangerous situations instead of a soldier. But I have had reports from people, anonymous sources, that people have literally died trying to rescue the robot because it was on their heads if the $1 million robot exploded. And yeah, so the solution I think that's appropriate for it is to choose your battles where you put actuation, where I think there can be a lot of passive systems that actuate, that like have a little bit of a bias. Like your foot is an example of this, where your foot is doing a lot of passive compensating for like what the dynamics of the walking downstairs or walking across rubble. Your foot is compensating for a lot of that just by being soft, and you bias it in small ways with the tendons and muscles that are in it. And so that's my belief, is that you choose where you've got springiness and compliance, and then you match that to where you've got your power for like locomoting and for, hauling stuff. Is that sufficiently answered? Yeah, does that feel pretty good? Thank you.
Okay. Oh, we have another.
Internet.
Are you a signal angel?
So
because we can't answer questions that are not asked on the microphone because we need to have them on tape. But we have the signal angel, and she has another one for us.
I have another follow-up question. We still have some time. So if you would need to trade off pneumatics versus
hydraulics, yeah.
I'm not
Pneumatics versus hydraulics, yeah.
Yes. So which would you use, or what was the use case for each of those?
Got it. So hydraulics are really good for things like mining. So you have like a drill that's being turned by a hydraulic system, and it has instantaneous torque, and you can get a whole lot of force, and there are relatively low line losses because of friction. That's a really good use case for hydraulics when you need instant torque and you don't want springiness. You can design springiness into hydraulics, but since water is incompressible, a piston that's being driven, like a hydraulic actuator, is exactly where you put it. So you actually have to to compress water. Water is technically compressible, but it's like on the order of like 0.0001%. But you actually have to to squeeze the hydraulic cylinder and get any spring out of it. You actually have to it ends up distorting the metal around it or blowing the gaskets. So that works interestingly when you talk about compliance systems, because you usually don't need as much this isn't going anywhere when dealing with compliance systems, but there are situations in which you want really instantaneous torque and things like that for being able to really quickly change the pressure inside of a system where you're someone has spastic motion in their arms, you're trying to exactly deaden it by returning pressure that exactly equals the opposite of that waveform. And so it's an interesting use case, but it's difficult to implement. I use pneumatics partially because I can be wasteful with it, where I can have things that are leaky, and it's just I just have a monitor on how much pressure is in the system, and I don't have to worry about how much I'm putting in, as long as it loops back to here's how much system pressure, here's the state of the system. It doesn't matter where the dial goes, as long as it stays at that state, it's fine. And so it's easy for me to have slightly sloppier systems that I can sort of fudge around with and create quick prototypes on and don't have to hunt down leaks. And that's why I use pneumatics, because that is a nightmare in hydraulics, hunting down leaks and stuff. And I don't want to be covered in hydraulic fluid every day.
Okay, first you're in the back, I think, because you have been raising your hand for so long.
Okay, you said your company is a NASA subcontractor, and
yes.
I think you said that you were using, or those gloves that you made will be used on ISS spacesuits?
If everything works.
If everything works. So obviously you believe in your product and
Yes.
you sold it very believable to me. But my question is, does NASA expect this to be the future of spacesuits, or are they just paying you to test around?
Noodle about. That'd be great. That'd be a great job. What'd you do? I messed about. Did it work? No. That's fine. So they're investing in this because they want to solve problems in spacesuits, and they think mechanical counterpressure is one of the ways to do it. Compliant materials like Playtex made the first functioning spacesuit that ever went into space. You know, not Northrop Grumman, not Boeing, Playtex, International Latex Incorporated. And it was professional bra seamstresses that designed and built the Gemini spacesuit. So the science, like the down and nitty-gritty science on soft materials, has always been difficult to evoke in physical stuff, but like having a gist of it, understanding the materials from working with them and applying them to practical problems has sort of been the thrust of most spacesuit technology. And so NASA is like, well, you guys, you work with this soft stuff. Can we do a new thing that hasn't been done before with spacesuits? And if it works, it could improve a lot of things and solve a lot of problems. But what's difficult in brand new systems is you're like looking at your ideals, and then you find out how it fails, like the externalities of it. And so we're exploring a lot of interesting things to try and solve these top-level problems, and the designs are evoking these sort of mid-level problems, and we're sort of hacking towards idealizing all of it. But the performance we see on the gloves, like the dexterity in vacuum chamber tests and the amount of pressure that you see, like the even pressure across the hand without like causing fingernail delamination, is really promising right now. And so it's encouraging NASA and it's encouraging us to keep pushing with it.
Hello.
Hello.
Yeah, you on the microphone.
We try to build some soft robotics in our makerspace in Milan, and it's very difficult. So I think that without having a design model to actually design the things before to build it, it's very hard.
Yeah.
So what do you think about the design process of soft robotics? Thanks.
Yeah. Unfortunately, there's no way I can give you like a data dump. It's almost like if you had to still copy C programming out of books, like if it was very hard to, like if the internet didn't exist and you still had to copy C off of books, you'd have thousands and thousands of people being like, why doesn't my program work? I've read the entire book. And it's like, well, you had a trailing slash here or something. Like there isn't a good guide to give you an intuitive knowledge of it without playing with it a bunch, because there's no real good wellspring of people who are jumping in to answer your questions. Like there's not a soft robotics forum. Well, there is on my website. But I actually have, if you go to superreleaser.com/forum, I actually do have a soft robotics, and I will answer your questions. But the difficulty is there isn't a level of knowledge up there to solve sort of meta problems of like, what's a good way to think about this? What are successful models of soft robots? And so like getting a base understanding to know why this didn't work and know what a successful soft robot tends to be designed like, and good design processes are thin on the ground. And I think that makes it a really huge ramp. You have to really get up the ramp of the learning curve really quick to be able to produce results to keep going. And I'm trying to solve that by publishing open source robots, make working designs and be honest about the design process, and then publish, what works and here's what to look out for. But before that's thicker on the ground and before people are available to just answer questions from people getting into it, there's almost no way you can do a data dump to somebody, be like, just read this book and then you will know exactly what's wrong with it. Because it, like many design problems, it takes having a detailed knowledge of the system in place.
Okay, I think we have one or two more questions from the Signal Angel again. IRC is working well, and we have still a lot of time left, so all your questions.
Yeah, people have been really fun, and they also want to thank you for the talk, as it was really cool. And one sees that you really have fun with this research. So the one thing people are still interested in, can you expand a bit on the $1 million robot being saved by the soldiers? Because that was really quick.
Sort of. So I don't want to talk too far out of my depth because I'm not in the military. I have friends, but I don't want to just be like, here's how it is, everybody. So in some ways, and this applies to all of the equipment that you use, if you're like an electrician, and you're servicing something, you're responsible for it. Even if someone directly working with you might say, well, that exploded, but it definitely wasn't your fault. Up the chain, it's your fault. And so when you introduce expensive equipment that people are nominally responsible for, if it fails, you have to find some way to justify for them why they're allowed to let it go. And so when there are some systems that star incredibly complicated and incredibly expensive equipment like a robot that's supposed to do certain kinds of field work, if it gets lost on your watch, you're nominally responsible and therefore have to take some of the heat for it. And so I think in certain situations when robots aren't 100% reliable, it ends up with people having to take responsibility for saving the robot, which is antithetical to their initial purpose. And so my theory is if you can get robots less expensive, if you can change the manufacturing principles of robotics, which is sort of one angle that I'm trying to go with soft robotics, is that it lowers that expense value, so raises that disposable robot, just it can blow up, that's okay, we can get another value. It changes sort of that equation.
Yeah, but they are not liable for them or have to pay if it breaks.
I don't think soldiers are individually responsible for. Honestly, I'm the last person you should ask about how the billing system works in the United States military.
Okay, thank you.
No worries.
Okay, we have more questions. You start popping up at the last seconds of the question and answering from the Signal Angels every time. I think you might have found out how not to stand all the time. The microphones, again.
Yeah, I have a question about going into production. Do you have any example of a project that reached mass market production?
A soft robotics project?
Yeah.
So the best example is actually NERF. So NERF uses a ton of soft compliant mechanisms to generate pneumatic pressure and to choose which dart gets shot in guns. They actually use a lot of soft compliant systems where it's like, okay, so you squeeze this and it conditionally will inflate that and that will go out to this particular rocket. Nerf gun. And compliant systems are everywhere. Sails are compliant systems. They conditionally stiffen based off of conditions. So based off of the wind and their direction, they will stiffen because the fibers have high tensile strength, and you can actually choose the shape of the sail based off of how you trim it. And that changes how much of a wing it is, and various other properties that allow it to go faster or slower and to be able to finely tune as you go over waves. That's one of the points of having a nerd talk. Anyway, it's one of the points of having a line on the edge of a Viking sail. So if you ever see illustrations of Viking ships, there is a line going out to the edge of a square sail. And you might be asking yourself, why the hell would you do that? Why wouldn't you just let the square sail be the square sail? And it's actually because the way Viking ships are designed, they are not self-righting. They are actually very tippy. And so when you go over waves, the boat flexes a little bit. And you need to change the shape of the sail and what direction it is taking the wind as it goes over waves by changing how aerodynamic the sail is, or else you flip over. And the reason I know this is because there was a book published from an anthropologist who studied Viking craft, made an exact copy of one, and kept flipping himself over because he forgot to have somebody trimming the sail.
Okay, one more question on the microphone.
All right,
one
I can do it.
One more. I don't know. We have still 5 minutes left. So if the RSC has more questions, of course. But first of all, him.
Hello. So you have soft actuators. Do you also have soft sensors?
Oh, soft sensors. So that's a thing that I'm working on as a background project. So there are lots of ways to use microfluidics as sensors to have a thing filled with a hydraulic fluid in a tiny little channel in a piece of silicone and read the pressure out the other end, with a little, a microsensing device. One of the difficult things about soft sensors is it's difficult to compensate for the flex of the system when calculating how much force is on it, because you can picture if you made a flat sensor array and you wanted to detect how much pressure a person, say you have a person with a amputation, residual limb is inside of a socket, you're trying to measure where the pressure is. So you have a flat sheet of sensors, and you stuff that into the socket, and the person stands on it. The sensor array is actually going to be detecting a lot of forces because of the particular order in which it bent, not directly because of the amount of pressure that it's experiencing. So one thing that is really difficult in sensor design is coming up with things that the orientation, like the way the sensor is accidentally stuck to the side of the cup in which you're trying to measure the force or whatever that is, it's difficult to compensate for that to make sure you're getting something accurate. And so one of the ways that people do that is by embedding stretch sensors in soft robots, and so they have like a linear measurement of how much stretch has been done. With the molding that I do, this is sort of an example of it. With the molding that I do, I can choose where to put individual electronic components inside of a soft thing. And so this is a ring that has a Trinket Pro inside of it and a couple of RGB LEDs. And those are in a specific spot in the silicone because they have a little rider board that actually slots into the silicone and locks in mechanically. And so you can, if you choose your battles with where you put your sensors, you can have them integrate with soft systems, but it ends up being a confounding problem, but one that a lot of people working in prosthetics and in spacesuits are working on and doing cool stuff in.
Okay, so the question is, Signal Angel,
All right.
do you have more for us?
Yeah, sure. People tend to get creative. So the last question from the IRC is, can you build pneumatic computers like state machines with this stuff, or do you always have to use a computer like interface?
Yeah, that's actually a question I'm really interested in, because the idea of doing pneumatic state machines, of having like something biased where you can have a series actuator where it's like this thing will only inflate under these conditions, and so you have like, this is the way octopus arms work. Octopuses are really cool. You end up taking a lot of soft robotic stuff from sea creatures. So when octopuses are panicked and trying to move all of their legs at once, they actually don't have enough processing to really do all legs flowing at the same time. And so if you see an octopus like pick up and run, it will actually limit the zone of solutions it's trying to find by creating straight sections in its legs. And so it'll actually create joints so it can physically run. And the way it has a distributed neuronal system. So octopus, individual limbs actually have their own processing centers. And so you'll notice they have a distributed brain. And so one thing that's really cool is that you can actually look at, with electrodes, you can look at what is happening in an octopus's limb as it's gripping something. And it's actually that you'll have these relay centers where it grips something with the end of the limb, and it'll be controlled by this functional relay center. And there'll be a signal sort of coming down and coming back from like the arm will have a relay center like the brain in a brontosaurus butt, and there will be like little nodes up. And what will happen is the nearest node will start the flex, and if another node gets hit, like as it's wrapping something up, if the next node gets hit, it'll continue wrapping. But if the next node doesn't get hit, it's gripping a small thing and it can discontinue the wrapping motion. And so what it's doing is it's sort of sending a signal back and forth and asking, where do I need to stop the wrapping? Wicca wicca. So to try and simplify the problem space. And so I think that would be really cool to do in soft robotics, to have these passive systems where you don't need a lot of signaling going on, to just have passive pneumatic, like that there's pneumatic logic inside of it. I think I've created a solution for that involves like this two-part molding. The difficult thing to do with pneumatic logic in soft stuff is you have to create check valves. And check valves are really hard to create without a spring. And when you cast something, you don't cast it in a spring orientation. It's hard to preload. And so it's very difficult, like if you imagine a heart valve, you know, the heart valve opens up. It's essentially a heart valve that looks like Shai Hulud. It's got like 3 actuating pieces. and they're actually all bigger than the hole, and so they fall back towards each other to create a check valve where pressure can't come back on the heart. It's very difficult to do that in casting because they open up, like you cast them in the opening orientation, there's nothing that springs back to cause them to close. But I think that I have created a solution for that with some complicated two-part molding to create things that get biased by another part that gets put in. But that's sort of like interesting theoretical soft robotics that currently doesn't pay the bills. So.
Okay, again, thank you very much for your interesting
Yay.
talk. We are all
Thank
out
you.
of time.